we are starting out with the idea of a limit. And again, the idea a limit is a value that you can get really, really close to. So here's our first look at what does it look like when a question has a limit in it, and what does this mean? So I would read this question as the limit as x gets close to 5. And then here we have the expression, and we have 3x minus 8. So this one, it should be really obvious. When x gets close to 5, it should get close to 7. Because if you plug in 5, 3 times 5 minus 8 is 7. If you plugged in something close to 5, like 4.99, it would be close to 7. So with limits, is if you can plug in the number, then you can evaluate it quite easily. So in this case, I could plug in 5, and we would say that the limit as x gets close to 5 is equal to 7. But we're going to find out sometimes you can't plug in that number. And then we're going to figure out how do we evaluate limits in that case. There we go. So a continuous function. With that example that we just looked at with 3x minus 8, if you were to graph y equals 3x minus 8, it would be a straight line. And this is not the official definition of continuous, right? In official definition, they don't say you can draw it without lifting your pencil. But that's an intuitive way of thinking of a continuous function. So for example, y equals 3x minus 8. Can you see that that's a straight line? And it would have a y-intercept at -8, and you could draw the whole thing without having to lift up your pencil. That would make it a continuous function. If you had something that was part parabola and then part line, and there was a big gap between them, there's no way you could draw both parts without lifting your pencil. That would make something have a discontinuity, or make it not a continuous function. So some examples of non-continuous functions that you've seen before, well, what about 1 over x? 1 over x has a non-permissible value at x equals 0. There's 2 parts to it, but you wouldn't be able to draw both of those parts all in one swoop. You'd have to lift your pencil to go from one part to the next. So we would say that 1 over x is discontinuous at x equals 0 and has a point of discontinuity or a value where it's discontinuous. Now, whenever you have a continuous function, or even a section of a function that's continuous, you can evaluate the limit just by plugging it in. So here, we'll have the limit as x gets close to 2 of x squared minus 1. Visualize x squared minus 1. Can you see that it's a parabola? Domain is everything. You could just draw the whole thing with putting your pencil down once. So in order to evaluate that limit, all we have to do is plug in 2. And when I plug in 2, 2 squared minus 1, it would be equal to 3. We can even do, we talked about we talked about 1 over x not being a continuous function because there's a discontinuity at x equals 0. So there's a problem at x equals 0. But at other points, you could, like if you looked at values bigger than 0, you could draw that section without lifting your pencil, or values less than 0, you could draw that section. So if the function that you're dealing with, you could plug in that point and not have a problem, not have a non-permissible value, we would say the limit as x goes to 3 of 1 over x is just 1 over 3. You can plug it in. So the basic idea says that if you can plug in that value, usually that's the limit. I can make up a couple examples that contradict that, but usually if you can plug in the value, that's the limit. And we'll get to see some strange functions in the future where that's not the case, but that usually is the case. And the reason that's the case is as we get a little bit further into the definition of a limit, what a limit's really looking at, for example, with x squared minus 1. Here's x squared minus 1. When I plug in 2, I have the point 2 comma 3. In order for a limit to actually exist at 2 comma 3, what you're going to be looking at is saying, if I get close to 2 from this direction, does it get close to 3? And if I get close to 2 from this direction, does it get close to 3? And if it does that from both directions, then we'll say that the limit does exist at that point. So for 1 over x, if I look at that graph, as I get close to 3 on this graph, I have the point 3 comma 1/3. And as I get close to it from the left side, it gets close to 1/3. As I get close to it from the right side, it gets close to 1/3. So therefore, the limit exists. The only time that you can plug in a value and it doesn't exist, and we'll see these, is let's say you have some weird kind of function that's a straight line this way with an open circle there, solid point there, an open circle this way. Okay? How would you write this function? Well, this is called a piecewise function because it has 3 different pieces. Yes?
What if there are horizontal lines?
Yeah.
Just one horizontal line, and it'll always be, it won't approach it at all.
Well, it would still, like if I had a horizontal line, okay, y equals 2. We could have the limit, it's a little bit silly, but we could say, what is the limit as x approaches 3 of 2? Well, it doesn't matter what x approaches, this is always equal to 2. And if you look at the graph that we've just drawn here, here's my point, 3 comma 2. As I get close to 3 from this direction, it gets close to 2. As I get close to 3 from that direction, it gets close to 2. Because it is 2. So it doesn't change. But in this one that I've drawn here with the different lines, let's say this is at 2 up here and this is a -1 down there. As x gets close to, right, the limit as x gets close to 3. From the left-hand side, it sure looks like it's getting close to 2. From the right-hand side, it looks like it's getting close to -1, but the definition says that it's equal to 1. In a situation like this, we would say that this limit does not exist. But we're getting into a lot more details than we're supposed to yet. So to start off with, if you can plug in the value, 99% of the time that's your limit. And that's going to be our goal. Can we set up an equation so we can plug in the value? So are we going to get a lot of questions like this? No, because that's plugging in values and figuring out what it's equal to. That's sort of like a grade 10 functions question. What do our questions start to look at? What happens when you have 0 divided by 0? Well, you're not allowed to divide by 0. Okay. So sometimes we have these places where things are discontinuous, like we saw with the 1 over x graph. And sometimes there's an asymptote in those graphs, and sometimes there's a hole. So here's an example from a grade 12 graphing question of something that has a hole. If we try to evaluate this limit right now by plugging in 3, can you see that the top would be 6 times 0, so the top would equal 0, and the bottom would be 3 minus 3, which would be 0. And so you'd have 0 divided by 0. And you can't divide by 0, so technically we can't evaluate this. But last year when we, or last semester perhaps, when you graphed these, you would have said, oh, well, these x minus 3's cancel out, and then my equation just becomes y equals x plus 3, and y equals x plus 3 is just a straight line with a slope of 1 going through a y-intercept of 3. But you still have a non-permissible value, and you would have drawn this with a hole at 3, 6. And that would have been the graph of y equals x plus 3 times x minus 3 all over x minus 3. What the limit is saying is if you tried to plug in 3 right away, you run into a problem because you have 0 divided by 0. But if I simplify this, then this equation becomes the limit as x goes to 3 of x plus 3. And now I can plug in 3. There's no problem. I'm not dividing by 0 anymore. So this is equal to 6. Graphically, we see why that happens, because our graph was that straight line with a hole in it. What happens when we get close to 3 from the left side or close to 3 from the right side? We get close to that point 3, 6. And so what your limit is finding, as x gets close to 3, what does your y value get close to? It gets close to 6. So this is the first actual limit type of question that we have. We have something with a hole or something with an asymptote, and you want to find out what y value it gets close to, even though when you plug it in originally, you're not allowed to do that. And that's where all of those skills that we had started from yesterday come into play. So that x equals 3 is a point of discontinuity. In the graph, we would say there's a hole in the graph, and the graph is undefined at that point. So when we get to these limits, we'll start off by trying to plug in the value to see what happens. So in this next example, if you plug in -2 on the bottom, you're dividing by 0. So what we have to do is use our skills in factoring and in rationalizing numerators and denominators to see if there's a way that we can rearrange this equation so we can cancel out the bottom, the part that's causing us to divide by 0, and then we'll be able to evaluate our limit. Often there's a hint in the question, but you got an x cubed plus 8. Can you see that that's a sum of cubes? We learned how to factor that yesterday. So if I factor the top, notation-wise, I have to keep writing the limit as x goes to -2 until I can actually plug it in and evaluate it. So for notation, I need to write this again. Now I can factor the top. And it just so happens that when you factor that perfect, or that difference of cubes on the top, you get a factor that's identical. And so now our equation just becomes the limit as x goes to -2 of x plus 2. And now, since you're no longer dividing by 0, you could just plug it in. And when I plug in negative 2, I just get 0. Oh, did I? Wait a minute. Yeah, there should be a minus, right? I have a mistake in here.
Yeah, I don't.
This should be,
Isn't it XY?
yeah, let's just re-go. Got a mistake. Sorry. This should be x squared minus 6x plus 8. Did I have a mistake in my notes, maybe? Because there's not, oh, okay. I'm trying to cheat. This is disastrous right now. Okay, are we ready? I was trying to cheat a little bit, but, okay, I'm sorry. But this is not x squared plus 6x plus 8. It's x squared minus 4x plus 4, right? And the bottom, 2x. Yes, wow. And on the bottom can be factored as well. And the bottom can be factored as what? X plus 2, x plus 4. I got overexcited about canceling something out, so I made it work. But what should cancel out is our x plus 2's, right? Yeah, that's right. Just making sure. Just want to make sure that things are good. All right. So now that we've factored correctly, and we've got the x plus 2's canceling out, we're still in that situation where we're not dividing by 0 anymore. Because our expression now is the limit as x goes to negative 2. On the bottom we have x plus 4, and on the top we have x squared minus 2x plus 4. If I plug in negative 2 now, do I divide by 0? No. So plugging in negative 2 now will get me a 2 on the bottom, and I'll have 4 plus 4 plus 4, 12 on the top. And so our limit as x goes to negative 2 is 6. Okay, now on the second time that we've done it right, are there any questions? So your factoring skills will come into play. Obviously they came into play today, and I screwed up royally at the beginning, but yes.
So you just try to find the coordinates of
The whole, yes. So now, you never had to graph ones like that in grade 12. But that one would have a hole at x plus 2. I mean, technically you could graph that using what you learned in grade 12, but you never did ones with an x cubed over an x squared. So this example, right now, with the limit, we're dividing by 0. Basically, what we want to do is we want to use our algebra skills to rearrange this to somehow get rid of that dividing by 0. Any suggestions?
the top is a line up. So you can just put both square roots or whatever. So that means h minus 3 squared minus 3, h minus 3 squared plus.
Good. So, one direction. He said the top is a difference of squares. Something squared minus something squared. And if I factor the top, oh, I like this. If I factor the top, I'm going to get h plus 3 times h plus 3, plus 3 in one place, minus 3 in the other place. Correct? H minus 3. Wow. I'm so good at copying things down today. So you have the plus 3 and the minus 3, because it's a difference of squares. Usually that's not the first thing people notice. What did someone else notice? Multiplying it out? Okay, good. Okay, so that's, now before we continue with that method, I'm going to say, yeah, that's another way. We could have said, let's multiply the whole top out. H minus 3 times h minus 3, that's going to give me h squared minus 6h plus 9, and then I still have minus 9 after it all over h. But I love this that you could see this in two different ways. Look what happens on the next step, no matter which method you used. In this one, when you simplify inside the brackets on the top, can you see that you're going to get just h left here and h minus 6 here? And that'll still be divided by h. On the right-hand side, if you simplify the top, you're just left with h squared minus 6h. And you could factor that, factor out an h, and both of them come to the same thing. Now at this step, we can simplify. Because we have a common factor, those h's cancel out. And as soon as you're no longer dividing by 0, then you can plug in your value to evaluate your limit. If I plug in 0 for h, I get negative 6, no matter which method that I used. So far with these limits, these 0 over 0 limits, what we've been looking at is initially you can't plug in the value because it would cause you to divide by 0. So what can we do algebraically to get rid of that so that we can plug in the value? So here's our last one that we're going to do. We've got a limit, which look at it, x equals 0. Obviously, if you plug that in at this point, you're going to divide by 0. So algebraically, we have to figure out what we can do. All the questions we've had up till now have used some sort of factoring. But we look at that one, and factoring might not show up. Yes. So this is where we say, well, we can rationalize the numerator. Maybe that does something. So if I multiplied the top by the conjugate and the bottom by the conjugate, we'll see what happens. Now, as far as simplifying things here, the purpose of rationalizing either a numerator or a denominator is to get rid of the square roots. And that's basically what's happening in this case in the numerator. So for sure, we're going to want to multiply our numerator out. Now you can put brackets around these and multiply everything out, or you can say, I recognize this as a difference of squares. So my first ones are going to be squared. And squaring a square root is just going to become x plus 16. And then it's going to be subtract my last one squared, minus 16. All over, and on the bottom, I'm not going to multiply it out because my goal is to get rid of that x. So it's kind of nice that it is factored that way, because my goal is to get rid of that x. Well, looking at the top, we just end up with x. And so our x's are going to simplify. Now be careful here, because often when you cancel everything out in particular, like here, there's nothing left in the numerator, right? We have to think, well, really, if we simplify x over x, that's 1 over 1. So take the extra time before you plug in 0 to rewrite this with a 1 on top. Because you will make the mistake of saying, oh, I'm going to plug in 0, and I'm going to get 8, and say the limit's equal to 8. But actually, when you plug in 0, it's equal to 8 on the bottom. And so the limit is 1 over 8.